Some sources report that the weights of full-term newborn babies in a certain town have a mean of 8 pounds and a standard deviation of 1.2 pounds, and that this is normally distributed. So part A asks, what is the probability that one newborn baby will have a weight within 1.2 pounds of the mean? That is, between these two values. Since we are told that this is normally distributed, we can answer this question by using the bell-shaped curve, which is a normal distribution. I'll go to question help to open up StatCrunch and bring that into the screen here. I'm going to go to where it says stat, choose calculators, and use the normal calculator. What I need to do is enter in the mean and the standard deviation, and then put in these bounds to figure out the probability. We are told the mean is 8 pounds with a standard deviation of 1.2 pounds. And we want the probability that is between two values. So I'm going to click here where it says between. And I'm going to go from 6.8, so that's 1.2 standard errors to the left of this mean. And this upper bound is 9.2, so that's 1.2 standard errors to the right of the mean. If I click compute, I get this number here. And it's asking to round it to 4 decimal places. And if I do that, I get 0.6827. So that was 0.6827. Okay. Now part B is asking for something similar, but just a little bit different. Part A was just, what if one newborn baby was selected at random? Well, how would this probability change if instead of selecting one newborn baby, we select 9? So we need a new sampling distribution to answer this question. I'm going to bring up a couple of formulas for this. So here we're going to use a sampling distribution for X bar, which will represent the average of 9 babies. It turns out that the mean of this new sampling distribution is equal to the one that we started with. So in using a normal curve to answer this question, the mean for the new distribution is the same as one that we started with. It's going to be 8 pounds. What is different is going to be the standard deviation. The sample size affects the new standard deviation. And this formula says, take the old standard deviation and divide it by the square root of the sample size. Here the sample size is 9, n is equal to 9. The square root of 9 is 3, so I'm going to take the old standard deviation and really divide it by 3. All right, let's put all this information into the calculator. So I'm leaving the mean alone, but I am dividing this number by the square root of 9, which means I'm dividing it by 3. Maybe just to see it a little bit better, I can do this on a calculator. So that is, I take the old standard deviation, 1.2, and I divide it by the square root of 9, which is really dividing it by 3. So 0.4. That is my new standard deviation. So I'll put that here. And we're still going between these two bounds of 6.8 and 9.2, so all I have to do is click compute. And I get this number here, which I'm also rounding to 4 decimal places. So that is 0.9973. All right, great. Now part C is asking, why are these two numbers different? What's going on here? So the distribution of means, so that's the thing that we did in part B. This is, well, it turns out it's taller and narrower than the original distribution. And therefore the distribution of means will have, let's see, so it'll have more observations located closer to the center of the distribution. It's kind of hard to see this because it's not scaled very well, but we're gathering up more information the same distance away from the center because the distribution became more narrow. So if I check my answer, that is everything that we need for this problem.